will start our class today. Last class, if you remember, we were discussing quenching of fluorescence and how it can be useful to figure out certain conformations of proteins, where the tryptophan is more exposed, where the tryptophan or any other chromophore is less exposed, right. Now, before ending the class, I also told you that we will be taking a break from fluorescence. That means, we have done a little bit of fluorescence, and the last topic in fluorescence that we want to discuss, or I want to discuss rather, is something known as FRET, fluorescence or Foster resonance energy transfer, which is very useful in studying conformational distributions or conformations in proteins, because it looks at the distance between two labeled sites or ends. So, however, before going into that, I think that would be the last topic we would cover in this course. I would like to digress and look at some other techniques, right, or other spectroscopic tools. So, one of the tools that is very much used in investigating proteins is infrared spectroscopy. Now, before going into the actual protein scenario, let me give you a brief introduction about vibrational spectroscopy. I am sure many of you know, many of you have already done it, but just to brush up your memories, we look at the theory. So, what we do is, when we are talking about vibrational spectroscopy, we are talking about vibration. Vibration of what? A bond between two atoms. Okay. So, this is say atom A and this is say atom B, A and B, right. Now, what we do is, because it is vibrating, because a bond vibrates, we treat it as a spring. Because we treat it as a spring, springs follow Hooke's law, then we have a certain potential energy curve, where the potential energy curve you can see is given by half k a square, or I can also write as half k x squared. Now, what is this x? X means the amount of stretching or compression I am doing with respect to the equilibrium bond distance, okay, or the equilibrium nuclear geometry. So, that means, if I have two atoms having a bond in between, so this is the R 0, which is the equilibrium distance, that is what the 0 in this graph signifies. So, this is the equilibrium geometry or the equilibrium internuclear distance. Now, what happens is, I can stretch the bond. So, once I stretch the bond, what will happen is, the distance is increasing and that displacement from the equilibrium position is being denoted as x. Okay. And you can see this red curve, this corresponds to half k x square, right. And what does A represent out here? You will soon see what A represents. So, if you go forward, what we do is, we treat this spring oscillation as a harmonic oscillator. That means, the spring is oscillating or vibrating, and we treat it as a harmonic oscillator. Okay. So, harmonic oscillator means, you can see how symmetric this curve is on both sides of 0, right, the middle axis, the middle y axis I mean. Now, what is A then? See, A is the maximum amplitude of vibration of the spring. Okay. So, that means, it goes to one position, the spring, it vibrates and it comes back and goes to another position, but these are the two maxima. Now, at the maxima, what happens is, at the maxima, because during the movement the spring would be having both potential and kinetic energy, at the maxima, which are its turning points, that means, because they are maxima, they have to come back. So, that means, if a spring vibrates and reaches this amplitude, it cannot go beyond. So, it has to come back from here, and it also has to come back from here. So, at these 2 points, the energy is fully potential. Okay. And at this point 0, the energy is fully kinetic, right. So, then what does half k a square mean? Half k a square means, where A being the maximum amplitude of vibration, this is the maximum potential energy you can have for the given spring, given the fact that A is the maximum amplitude of vibration. So, you can understand at the turning point. So, this is a turning point. So, this is the turning point. This means that the spring cannot vibrate beyond this. At the turning point, because the energy is totally potential, that means E is equal to half k square, right, and at the bottom where you have totally kinetic energy, then E will be equal to the kinetic energy, and in between it is a mixture of both. Okay. Now, this is a very important characteristic parameter which is known as the vibrational frequency, that is nu. So, nu is given by 1 by 2 pi root over k by mu, where k, if you remember, is referred to as the force constant and mu is referred to as the reduced mass. Okay. And what does reduced mass refer to? So, reduced mass is actually a combination of both the masses m a and m b or m 1 and m 2. So, that is it is an expression. So, mu can be given by an expression which involves both the masses, right, or we can write 1 by mu is equal to 1 by m a plus 1 by m b, right. So, this is how mu or the reduced mass is given. So, this is the characteristic vibration frequency. Now, mostly when we are talking about vibration bands, we do not express in terms of frequency, rather what we do is we express in terms of wave numbers, right. So, wave number is given by this expression. So, this is a corresponding wave number. If this is the frequency, this is the wave number, right, is equal to 1 by 2 pi c root over k by mu. Now, obviously, we will understand that this wave number, which is the centimeter inverse, that is the unit we mostly use, we still refer to it as frequency, okay, though it is not absolutely right in terms of the nomenclature, but it does not change much, because if you would keep in mind, energy is equal to h nu or delta E is equal to h nu, right, or we can also write delta is equal to h c nu bar. That means, in both cases energy is proportional to the either the frequency or the wave number. So, anyway, the bottom line is that if you are looking at any vibrational spectroscopy, you will see that the x axis is in terms of wave numbers, but still we end up calling it as frequency. Okay. So, this was a very brief intro about introduction about this vibrating bond. Now, just one more thing before we start looking into vibrations. So, you can see this is another plot where you have two potentials shown. One is a harmonic potential, which is given in green, and the other one is a Morse potential, which is also known as an anharmonic potential. So, this is also known as an anharmonic potential. Okay. Now, what is the difference? As you can see, the harmonic potential is absolutely symmetrical. The anharmonic potential, however, is not, because if you go to very high internuclear separation, that is what I said, internuclear separation. If you go to very high internuclear separation, which means that you are stretching the bond like anything. So, you do not expect the bond to remain stretched and nothing happen, even if you do it for a huge distance, which means that after a certain distance the bond will snap or break, and because the bond will snap or break, you can see what happens. This is something referred to as a dissociation energy. That means, what it says is, if you go to this energy, because energy is on the y axis, if you go to this energy, the dissociation energy, if that is the extent of vibration energy you are putting in, and if the molecule is there in terms of its vibration energy, that means it is vibrating so fast, it is vibrating with so energy. So, what will be happening is the bond will break and the molecule or whatever, this bond will dissociate, right. That is what it means. However, if you look at the harmonic potential, you do not get this bond dissociation picture. So, this Morse potential, which is also the anharmonic potential, is the real potential that a bond would face or experience during vibration. Okay. Now, there are other implications to this. For example, I will just give you one thing before I move out of this slide. So, for the harmonic potential, if you see, the energy levels are all equispaced. You can see the energy levels for the harmonic potentials, which are in green, are all equispaced, if you can see. However, if you look at the anharmonic potential, which are given in blue, so you can see the energy levels start, there is a wide gap from bottom. So, nu is equal to 0, nu is equal to 1, but as you go up, what is happening is the gap in between the energy levels is decreasing, and once you reach the dissociation energy, the gap is really small, because when you dissociate, what happens is you are almost in the continuum of energy levels, because there is almost no quantization now that the particle is free, right. So, I am sure these things you already knew. It was just a brief recap of what you have done in your spectroscopy course. So, let us quickly look at the different infrared spectral regions that we have. So, one is the near IR, the wavelength from 0.78 to 2.5 micron, and the wave number, okay, this is the frequency we actually refer to, is 12,800 to 4,000 centimeter inverse. The mid IR, this is the one we are going to be concerned with. It is 2.5 to 50 micron in terms of wavelength, and 4,000 to 200 centimeter inverse in terms of the wave number. And there is a far IR 2, which is 50 to 1000 micron or 200 to 10 centimeter inverse. So, this is the one, the mid IR, which we are going to focus on mainly. Now, let us look at some vibrations. So, this is an example of two types of stretching vibrations. One is a symmetric stretch, because you can see both the arrows are pointing towards the same direction. The other one is antisymmetric stretch, because in one case you are compressing the bond, in one case you are stretching the bond. So, that is why these are called symmetric and antisymmetric stretching vibrations. Then there are bending vibrations. Stretching is not the only thing you can do, a bond can even bend. So, you can see what happens is, this is all these bending vibrations are in plane, that means occurring in the same plane. So, scissoring means, so this is, as you can see, this is moving towards like a scissor, this is moving towards this direction, and this bond is moving towards this direction. So, it is like a scissoring effect. The rocking is, while in scissoring both the bonds were moving towards each other like a scissor, as you use a scissor to cut something. In the rocking, you can see both the bonds are moving in the same direction. So, that means it is like a rocking chair, you are rocking, you are moving back and forth. But remember, both these things are in plane. And what about then if you have a set of bending or in plane bending vibrations, then you are sure going to have some out of plane bending vibrations. So, what do if you look at this figure, what do the plus and minus refer to? Plus means you are vibrating above the plane, and minus means you are vibrating below the plane. So, if you can look at this, so the first one, this is plus, right, and this is also plus. Plus means both are above the plane. So, it is like wagging of a tail. So, you are wagging, okay. Remember, this is out of plane, you are coming out of plane, but both the bonds are moving in the same direction, right. Now, in case of twisting, however, the opposite thing is happening. One bond you can see is moving out of plane, that means above the plane, and this bond is moving below the plane, right. So, this is a case of twisting. So, these are different out of plane bending vibrations. So, here again we look at them together. The first two you can easily recognize, asymmetric and symmetric. The next two in plane bending movements, scissoring, rocking, and the next two twisting, wagging, which are out of plane bending movements, the thing we just discussed. And to stress the fact again, you can see this is another similar figure, which again enforces the fact what are the differences between the different types of vibrations, the symmetric, asymmetric, in plane rocking, in plane scissoring, I mean these are in plane bending vibrations, then out of plane wagging and out of plane twisting, right. So, the last two are bending vibrations, the first two are, the last four are bending vibrations, the first two are stretching vibrations as shown out here. Okay. So, whenever we talk about a vibration, right, whenever we talk about vibration, these are broadly defined, the different types of vibrations that can be present. Now, when we go to a protein molecule, all these types of vibrations would be there, but what are the types of vibrations we would be really interested in if we want to look at a protein folding, unfolding or different conformational aspects? That is what we are going to focus on. Okay. So, these are some examples of molecules before we move into proteins. So, for example, this is for H2O, right. So, this is the oxygen, this is oxygen obviously, and these are the two hydrogens, right. So, this is also hydrogen. Now, you can see this is symmetrical stretching, the first one. The second one is asymmetrical stretching, and you can see why it is so. In the symmetrical stretching, both these arrows, in the symmetrical stretching, both the arrows are pointing in the same direction, right. In the antisymmetrical stretching, it is just reverse. So, this arrow is pointing in this direction, this arrow is pointing in this direction. That means, in one case you are stretching the bond, the other OH bond is getting compressed, and this is a scissoring, which is a bending vibration, but still in plane, right. Now, the other one or the other example is for CO2. You can see the first one is an asymmetrical stretching, the second one, or well, yeah, the second one is a scissoring or bending in and out of the plane. So, the plus and minus, remember what we talked about. Then just below the bending in and out, we have the scissoring, which is the bending in plane, and to the extreme left bottom is the symmetrical stretching. So, these are the different vibrational modes of CO2. Now, what about the vibrational modes in proteins now? Because this course we are mainly interested in the proteins, how to study their different conformations and many other aspects. So, one of the vibrational modes, and I will tell you what they are and what I mean by these. So, the first one is referred to as amide A and amide B. These are different vibrational modes. The second one is amide 1, and this is in a different color, because this is the one we will be most interested in and will be most discussing about. The third one is amide 2, and then you also have amide 3. So, these are the different significant modes of vibration which are present in proteins, and as I said, or as I told you, the amide 1 is the one we are going to spend some time on. Now, if you would like to model the vibrations, then you have to start from a very simple molecule, right. So, the simple molecule we start with is called N-methyl acetamide, and you will see why it is the one which is being used, because you look at it, a peptide has many amino acids, right, but in this case you can see N-methyl acetamide, it is just one small unit, and if you are going to do calculations on this, then you will be having very accurate calculations. So, this is called N-methyl acetamide. It is the smallest molecule containing a trans peptide group, and it is the starting point for normal mode analysis. Now, if you would remember normal modes, like if you have these translational the translational modes, rotational modes, and then the other modes of vibration, people do normal mode analysis, right. You must have done during your group theory course. Then for N-methyl acetamide, the number of normal modes is given by 3n minus 6, which is equal to 12. Now, this we know, the 6 comes from the fact that you have 3 translations x, y and z, and 3 rotations x, y and z again. What is n? N is the total number of atoms I have in the molecule N-methyl acetamide. Okay. So, here what we have out here is it is 3n minus 6, which is equal to 12. Now, moving on. So, that means in N-methyl acetamide we still will be having 12 normal modes, not 1, not 2, but 12 normal modes. Okay. What about amide A and amide B? So, amide A and amide B are essentially NH stretching vibrations, right. So, they range between 3310 and 3270 centimeter inverse. They are localized primarily on the NH group, NH stretching vibrations, that is what they are. It is not sensitive to the conformation of the polypeptide backbone. Now, this is a problem, because see, if you are in proteins, you mostly are interested in changes in conformations, which is the backbone, alpha helix possibly changing to beta sheet, or alpha helix changing to a random coil, or beta sheet changing to alpha helix or a random coil. And if this mode is not sensitive to that change, then you would not be looking at this mode, right, to see what is going on with the protein conformation. And the frequency obviously depends upon the strength of the hydrogen bond, because it is an NH stretching vibration. So, you can understand, if you change solvents, it would be affected by the solvent, because that is how your hydrogen bonding interactions would change. Now, what about amide 1? As I said, this is the one we are going to be primarily concerned with. So, amide 1 is primarily from the CO stretching vibration. Remember the peptide bond, we have a carbonyl group. It is primarily the CO stretching vibration which constitutes the amide 1 band, but along with that there are small combinations from in plane NH bending vibrations of the peptide backbone. Okay. The CO stretching vibrations, it will these absorb near about 1650 centimeter inverse in proteins or peptides. These are not affected by the nature of the side chains of the amino acids. Okay. However, this is a very important point, the last point is very important. Why is it important? See what it says. These stretching vibrations are very sensitive to the secondary structure and hence conformation of the polypeptide backbone. Okay. Thus, it is the most commonly used vibrational mode for conformation analysis. Now, see what it means. What it means is this aspect was not available for the NH stretching or bending vibrations, right. But when we are coming to the CO, which is the amide 1 mode, the CO stretching, which primarily constitutes the amide 1 mode, what we are saying is it is very sensitive to the conformation of the polypeptide backbone. Then obviously, you can understand that if it is so sensitive to the polypeptide backbone, then obviously, this is the one we should be looking at, or one should be looking at if you have to do some protein conformation analysis. Okay. So, this is again what we are talking about. So, if this is a certain protein, right, and you can see this is kind of a beta protein mostly. Now, you look at this mu, if I can show you with the arrow, this mu is your corresponding amide 1 transition dipole moment. Now, see, though I said it is CO, it is not exactly aligned along the CO. However, it is at a certain angle because you have some contributions from these NH in plane bending modes, right. But one is that, so this is the type of dipole moment you are looking at, but the second issue is you look at this scale. Now, this is very important. See, proteins will be having different conformations, right, either alpha helix or beta sheet, combination of both, random coil if you would denature a protein, or if you are taking any unfolded protein, then using the amide 1 band, can I try to figure out which one is which. So, this is what it says. You can see the red one is the alpha helix. You can see alpha helix is in between 1640 to 1660 centimeter inverse. Then you have the random coil, which is kind of in the same region. Then you have the beta turn, which is at 1680, beta sheet, and beta sheet. You can see beta sheet occurs at two places because it has two antiparallel beta sheet. When you are looking at aggregates, it has essentially two bands, one at about 1620, 1625 centimeter inverse, and the other one at about 1680. Now, all these different patterns or all these different bands are characteristics of these proteins, different proteins, whatever structure you are referring to. So, that means what you are trying to do is, if you have an helical protein, you would be having a certain IR signal or spectrum. If you are having a beta protein, you would be having a certain signal. If you are having aggregates, protein aggregates are the root causes of many neurodegenerative diseases like Alzheimer's, Parkinson's. Now, if you want to look at the aggregates, protein aggregates, how they are aggregating, if you want to look at the protein aggregation kinetics, then in those cases the bands you would be looking at are two. One is the 1625 centimeter inverse, which is a pretty well developed band, and then there is this very small band at 1680 centimeter inverse. This characteristic of antiparallel beta sheet aggregates. Okay. Now, to look into it a little more detail, the first question that comes to your mind is, okay, I understand that my amide 1 mode is so sensitive to the protein secondary structure changes. Why is it so, or how should I understand, or how should I try to understand its sensitivity to such changes in structure or conformation. Okay. So, let us look at this first. The transition dipole coupling is the fundamental mechanism that makes the amide 1 band sensitive to secondary structural changes. So, obviously, you think about these three words, transitional dipole coupling. We have already looked at the transition dipole in the previous slide, which was mu, which means is once you have a transition dipole, this dipole has to couple with other dipoles. Now, where will these other dipoles come from? Very simple. So, when we are talking about N-methyl acetamide, we have just only one unit and we have one dipole, right. But when we are talking about a polypeptide or a protein, we will be having many amino acids depending upon how big or small the protein is. So, now what will happen is all the individual transition dipoles of these CO groups would be coupling with each other to give rise to the actual spectrum you are seeing, and that is what brings around the sensitivity. Okay. This is the root cause of the sensitivity of your of the amide bond band to conformational changes. That means, all the transition dipoles coupled with each other remain delocalized over the whole protein moiety or molecule, and they change or they are sensitive to any conformational changes which are occurring. Going further, what is it arising from? As I just said, it arises from resonance interaction between oscillating dipoles of neighboring amide groups. What it means is, so you will be having one dipole, say number 1, number 2, number 3, number 4, so on. Number 1 will interact with number 2, number 2 will interact with number 3, these are adjacent, number 3 and number 4, like that. But see, number 1 is also interacting with number 2, 2 is interacting with 3, in one sense 1 is also interacting with 3. That means, every dipole is getting affected by the other dipole to some extent or the other. But however, what will coupling depend upon? As you can understand, the neighboring groups would be having the maximum kind of interaction or coupling. So, coupling depends upon the relative orientation, obviously how oriented they are in terms of the geometry, angle and the distance between the dipoles. So, the dipole distance, if you would recall, the type of this van der Waals coupling or dipolar interactions we had looked at before, always we had this term or this dependence on the distance between the dipoles, right. So, in this case too, if you are talking about dipolar coupling, then you have to talk about distance, and what it means is, the larger the distance, the lesser is the coupling, or the smaller the distance is, the more is the coupling. Then obviously, it is strongest when coupled oscillators vibrate with the same frequency. Now, that makes sense. Now, let us look at the transition dipole again. So, here this is a zoomed into picture. Okay. Now, you can see how the transition dipole is. So, this is the CN bond, this is the CO bond. You can see the arrow of the transition dipole. Do not worry of the broken arrow, it is not of much consequence out here, but this arrow, this is typically how the transition dipole is aligned, right. So, the solid arrow represents the transition dipole, and if you would just reorient, that means, if you would just change the orientation of the molecule, and this is how your transition dipole would look at, and please make sure that this is what we are talking about is the amide 1, right. This is the amide 1 band or amide 1 vibrational mode we are talking about. Okay. Now, here you can understand in this case, so this is CO, so this one is CO, right. Here this one was CO, you have just changed the orientation of the molecule, but look at this, you look at this angle of about 20 degrees. So, what it is saying is, that the dipole is so oriented that it is at about an angle of 20 degrees with the CO axis. Okay. So, it is just not perfectly aligned along the CO axis, because it is minor contributions, but though minor, these do change the orientation from the NH in plane bending modes and others. Okay. So, this is the transition dipole on one unit, that means, on one peptide unit, on one amino acid I mean. Now, think about this, because you have a sequence of amino acids, all or each and every amino acid will be having this CONH bond with the neighboring, that is what it will have from the peptide backbone. That means, there would be so many, and each of these would be coupling with each other. So, that the whole effect is kind of a delocalization of these interactions over the protein molecule. So, obviously, when you are talking about the CONH bond, then as I said, we are going to talk about the interaction between the oscillators, because that is what dipole coupling is all about. And just to take a quick look, this you have looked at before. So, this is the interaction potential or the interaction energy VAB. You can see what it is depending upon. It is depending upon the mu A, mu B, obviously, which are the dipoles associated with your oscillators, and look at R, you have this R cube dependence. Okay. So, just to explain it a little more, VAB, it is the interaction energy between the transition dipoles of oscillators A and B, right. These are two different oscillators, like two adjacent amino acids or two neighboring CONH groups I mean. Mu, the corresponding transition dipoles of A and B, the oscillators, and what is R? R is the distance between the oscillators. Okay. So, this is the typical interaction energy you are looking at. Now, think about this again, there will be so many A's and so many B's, not only A, you will be having A, B, C, D, E, F, G, H depending upon the number of amino acids you have again, and all these will be having their own interaction energy, right. So, it will, so obviously then it will be a very well developed interaction. Okay. Now, coming back to the amide 1 positions again, what the table shows you is the characteristic amide 1 position of your IR spectrum, that means the peak of your IR band for a given secondary structure. So, look at this for alpha helix. Now, pay attention to this, there are two columns out here, right. One gives you the band position, that means the IR band position in H2O, obviously in centimeter inverse. The other one is 2H2O, which is heavy water, which is deuterated, that means D2O. We can also write that. Now, why we are talking about D2O, this will become clear later as we move on with this discussion, but first let us look at this. For alpha helix, the average is about 1654 centimeter inverse and the extremes are from 1648 to 1657. Now, when you go to 2H2, that is D2O, then the average becomes 1652 and it goes from 1642 to 1660. Okay. Now, beta sheet again it will be having 1633 as the average in 1H2O and the extremes are 1623 to 1641. Also, you can look at this, there is another band at 1684. Now, this is typically observed in antiparallel beta sheet aggregates, right, and these are the extremes which are given. The second column obviously are giving you the corresponding frequencies in D2O, then you have turns and then the disordered regions, right. Okay. So, this is now it is not that you will always have to go by this and this will always be maintained throughout, but at least this is a guideline for you to understand what is going on when you are saying starting with an alpha helical protein, you are denaturing the protein, how is the spectrum going to change and all those things, this is what is going to let you know. Okay. So, here is we are looking at kind of a complete spectrum from protein. So, you are looking at what? You are looking at the amide 1 stretching, which is the CO stretching. Then there is amide 2 we have not yet talked about, and then there is amide 3 stretching. Okay. As you can see, these are mainly the modes which are shown out here, C and NH and all these things, but we will look at this later, right. But let us talk about the amide 1 mostly. So, as you can see out here, this is the amide 3, this is the range of amide 3, it is given, this is the range of amide 3. Okay. Now, this is the range of amide 2, it is coming out here, and then amide A, remember this is what we started with NH and obviously the NH. So, this is where this one comes, and then this is the one we are interested in, and this is the region we are mostly going to talk about or focus our discussion on. Now, let us look at a typical amide 1 band. Okay. So, this is the black line shows a typical amide 1 band or shape coming from a certain protein. Okay. We do not know what the protein is, we do not have to know, this is just an example. So, that means you have taken the protein, you have taken the IR spectrum. Now, let us not worry about how what are the experimental issues, how should we do this experiment, we will discuss those slowly. But anyway, what it says is that if you are given a band like this, an experimental band, now see the experimental band is very broad. Now, why is it broad? It is broad because as you can see, if you would remember the alpha helices, the disordered structures, the beta sheets, they have many overlapping, they are very close to each other. What you looked at were the central frequencies, right, that means the maxima, but they will be having their own widths, right, and hence they will be overlapping. So, all this will be merging together. So, how would you extract useful information from a given experimental band? The way you do it is you do a deconvolution, that means you try to deconvolute or try to extract the information out, that means you try to decongest or deconvolute, that means you try to take the information out from the given experimental band. How do you do it? What you do is you fit this spectrum to a set of Gaussians or Lorentzians, whatever you want to, right, and then you try to figure out how much of alpha helix I have, how much of beta sheet I have, how much of random coil or disordered structures I have, how much of turns I have, like this. Now, these are nowadays done very regularly, very frequently, and you can see what what you have under this experimental band. So, under this experimental band shape, the black one, you can see you have 4 typical Gaussians. Now, what are these Gaussians corresponding to? Say for example, this band corresponds to an alpha helix. Okay. So, that means because this one almost has say the maximum intensity and almost all the maximum area, that means mostly under these conditions your protein is alpha helical in nature. Okay. Then this is the random coil, okay, and the rest is the beta sheet. So, this is how what you have tried to figure out. So, that means by fitting your experimental band shape to a combination of these 4 Gaussians, you have tried to figure out how much of percentage I have for belonging to alpha helix, how much of the protein in terms of percentage belongs to the random coil, and how much of the conformation in terms of percentage belongs to the beta sheet. Now, this is typical of any protein you would take, mostly would be getting experimental band shapes which are pretty broad, but because you know from the previous table what the central frequencies are for your beta or alpha, then you can actually deconvolute it using Gaussians to try to get the percentage information of helices, beta sheets, random coils. Now, to move on, let us look at a typical protein. Now, we are talking about a specific protein. This is lysozyme, and you can see the lysozyme is mainly alpha helical, right. You can see mostly alpha helices, right, and there are some surface exposed beta sheet regions. For example, you can see this one, this is a beta sheet. So, what it means is you will definitely be having alpha helices mostly, and then also having beta sheet, right. Now, this is the amide 1 band of native lysozyme. See how complicated it is, you are trying to deconvolute it. So, which was the amide 1 band? So, this black one is the amide 1 band. You are fitting the amide 1 band to 6 Gaussian spectra or 6 Gaussians, right, to a sum of 6 Gaussians. What are the different ones? One is alpha helix, as I said, you are going to expect that because that is predominant in the structure. Then you have beta sheet, then you also have the random coil. Okay. So, that is how you have to try to extract information out of this experimental band shape using this deconvolution method. Now, suppose you take the same lysozyme and you denature. Now, the moment you denature, what happens is you can see there has been a change in spectral shape, right. Initially it was like this, and the experimental band shape has changed. Now, because the experimental band shape has changed, and we have discussed this at some length before, that a denatured protein is much more flexible, is much more disordered obviously than a native protein. So, you can understand that possibly we will be needing some more Gaussians or more bands to fit the spectrum, and that is what you have what it has been tried out here, and there you can see people are using about 8 Gaussians to try to make some sense or try to figure out or try to kind of get some usable information from the experimental band shape, right. So, the underlying message is that if you are given an or if you are given an IR instrument, you take an IR spectrum, you take an FEIR spectrum. Now, once you have taken the spectrum, then that is just not it. You will have to do a band analysis, you have to do a decomposition, people also do second derivatives and all these things to get useful information out. But if you know what you are doing, then in almost all the cases it is very, this thing is kind of very well developed. You know what you are looking for. If you know what you are looking for, then you do not have much of a problem in trying to figure out what different conformational changes I am having to deal with. But let me tell you one thing, proteins aggregate, and when you denature proteins, because you are exposing hydrophobic groups, depending upon the tendency of the protein or the the number of hydrophobic groups, the protein can either have a small tendency to aggregate or you can have a huge tendency to aggregate. Now, many proteins do aggregate at these denaturing concentrations, and what will happen is if you would increase your denaturing concentration, because you are exposing more of the hydrophobic groups, that protein which has a more of a tendency to aggregate will actually start aggregating, and if they are forming antiparallel beta sheets, then what you will see is you will see this, you can see this 1625 band and this 1687 band. These are typically coming from antiparallel beta sheet aggregates. Okay. Now, is this all what it is? No, many side chains also contribute, but we would not be going into that much details. What I will do is at the end of my discussion on IR spectroscopy, I will give you some references. I think these references are extremely useful for anybody working on IR spectra of proteins, for them to have a logical interpretation of a logical insight of what we can have under the experimental band shape. So, again before leaving this slide, the denatured lysozyme has been fit with 6 Gaussians, right, or rather 8 Gaussians, and the native lysozyme was fit with 6 Gaussians. Okay. Now, let us move into some experimental considerations. Now, what experimental considerations are looking for? Suppose you are going to do an experiment, suppose you are going to measure an IR spectrum with a protein or of that of a protein. Now, what is the major advantage of FTIR spectroscopy? One of the major advantages is one can use both liquid and solid protein samples. So, it does not matter. So, suppose if you have a liquid protein sample, good. If a solid protein sample, which means that your protein is not that soluble, or it is hard for you to get a liquid sample, whatever, but still you would be able to get an FTIR spectrum. Now, would that FTIR spectrum of the solid sample be same as the liquid sample? Now, that is a different issue altogether. I am not saying it will be, differences are always found, there are reasons for that, but at least you can, if you have a solid sample with you, you would be able to take a spectrum of that. So, liquid samples can be done using transmission IR. It is like your absorption measurement. Here you do a transmission and then you convert it to absorption absorbance units. For solid samples, you can use ATR FTIR. So, one is transmission FTIR for liquid samples, the other one is ATR, attenuated total reflection, internal reflection essentially. We will talk about this again very briefly, what this ATR technique is and why it is so beneficial. Now, majority of the FTIR studies of proteins are performed in aqueous solutions or suspensions. Okay. Now, it makes sense, right, because your proteins, your physiological environment in your body is water, a huge body mass percentage is water, and obviously almost all the proteins are in water, right. So, it makes sense then for you to take the IR spectra of proteins in water, or if some protein is not soluble in water, then you take in aqueous suspensions. But that is where the problem starts. What is the limitation for aqueous solutions? Now, water has a strong OH bending absorption at about 1644 centimeter inverse, which masks the amide 1 band. Now, if you would remember, I will show you in the next slide, the amide 1 band was kind of centered around 1650, right. I mean, it is an average position we are talking about. Now, the OH bending, if it has a very strong OH, if water has a very strong OH bending in that position, which is the 1644 centimeter inverse, then what will happen? It will try to mask your amide 1 band. Okay. So, adequate subtraction. So, now what you can do is you can say that, okay, I will do a background subtraction and make sure that after subtraction the spectrum I have is that because that of the protein only. Now, adequate subtraction, look at the second point, adequate subtraction will only be obtained if the spectra of the protein solution and water or buffer in case of proteins are recorded at the same temperature due to the strong dependency of water absorptions on temperature. Hence, using temperature controlled cell holders is preferred. Now, this makes sense. You just cannot take the IR spectrum of the background, which is water in this case, no protein sample or buffer at one temperature, and take the protein sample at another temperature, because your intensities would be different. You cannot do a background subtraction. So, the idea is that if you are going to do it, you make sure that your cell holder is temperature maintained, okay, for a proper subtraction. Now, this is the IR spectra. This figure shows the IR spectra of protein in presence of water and D2O. Now, look at this. This is your amide 1 band, right. So, this is the region I am interested in. So, this you can say is 1600 to 1700. So, again this is the region 1600 to 1700 centimeter inverse. Now, look at this amide 1 plus H2O. Now, look at the intensity of this. Okay. This amide 1 plus H2O, sorry, my arrow is becoming too broad. You can see what the intensity of this band is in terms of absorbance. It is pretty high. Now, this is for a protein in presence of water. So, the protein also has its amide band here, and it is in addition to the bending, that OH bending mode of water. But look at what happens in case of D2O. So, when I am talking of this amide 1 prime, amide 1 prime means that I have now taken the protein and put it in D2O. That means all the hydrogens have been exchanged and replaced by D, that is what the significance of prime is. So, if you do not have prime, that means it is an H2O, if you have a prime, that means it is D2O. Okay. Now, see, the moment you take it in D2O, how much the absorbance is increased out there. Now, what is the reason? The reason is, and I will tell you later, that once you replace H by D, then the vibrational, that OH, that OD bending mode is far shifted out from the amide 1 region. So, the background from this D2O or OD bending is really low at the amide 1 position. So, you can understand that if you are going to do a transmission, and if you would be having say a long path length, smaller protein concentration, you would rather use D2O than H2O, because for H2O the longer the path length you use, the more will be the absorbance and the more will be the masking over the amide 1 band. In that case, your subtraction is not always proper. Okay. So, what were the path lengths used? So, let us look at this. The for taking the water spectrum, the path length was 6 micron, right, and for taking the D2O, so this was transmission, for taking the D2O, the path length was 20 micron. Okay. Now, again look at this, your water was just 6 micron, so almost 3 times less than that of the path length of D2O, but still see the intensity of the amide 1 band, which means this amide 1 band already has a huge amount of contribution from the OH bending. Now, as we were discussing, problems still remain when studying proteins dissolved in water or aqueous buffers due to the high molar absorptivity of the OH bending vibration of water, and problems associated with detected linearity. Now, you might think that okay, it does not matter, I will take only the water and I will take only the protein. I will take first the spectrum of water, I will take first the spectrum of protein, I will do a proper background subtraction and it will not be a problem. But the thing is that your background subtraction might not be proper, because the detector response to the water concentration or to that high absorbance might not be linear, and then obviously your background subtraction is not the way you want it to be. So, this limits the path length that may be used in studies of proteins dissolved in water to 10 micron or less. So, you can understand if it is more than 10 micron, what is going to happen? The detector will not be giving a linear response to your change in water absorbance, and if it is not going to give you a linear response, then how would you have a proper workable background subtraction? You cannot have it. So, longer path lengths result in significant distortions of the water absorptions, making proper background subtraction quite difficult. This is what we just said. So, as you can see, if you are going to use protein in water, you make sure that the path length is really small and the protein concentration is high, because if only the protein concentration is high, would in the amide 1 band be a huge amount of protein contribution. Now, let us look at it a little more deeply. Now, obviously, what is the remedy? The reduction in path length requires very high concentrations of protein solutions, because see, if you would remember your Lambert-Beer's law, what is Lambert-Beer's law? Absorbance is equal to F silent, the molar absorptivity, molar extension coefficient, I am C into L, C is the concentration, L is the path length, the longer is the path length, right, the more is absorbance. The same thing will happen here. However, what is the problem? The problem is that you can increase the path length, go for a small protein concentration, but if you are doing it in water, the water absorbance would increase proportionately, right, again you will be running into a problem. So, you go for a smaller path length, as we just looked at in the previous slide. Now, even if you go for a smaller path length, that means to get a workable, or what should I say, a decent or sizable contribution or significant contribution from the protein amide 1 mode, you have to make sure that you have taken a huge amount of protein concentration depending upon the size of the protein and the nature of the protein. Now, this is not always so easily done. One, proteins are sometimes not available to that extent, because proteins can be very expensive to work with. Number 2 is some proteins are very prone to aggregation. So, if you increase the concentration, then they would easily aggregate. So, you would not be able to do the measurements you wanted to do with the protein. So, then obviously, the remedy is, again, if you are doing transmission measurements, all these are talking about transmission measurements. I am not talking about any of these reflection measurements, that means they are on the solid sample or pastes. All these are transmission IR measurements, FTIR measurements I am talking about. So, you use D2 as a solvent, as you just said. The OD band is shifted out of the window to about 1205 centimeter inverse. This is the bending I am talking about, the bend in this case that is what I am saying, not bend, thereby making the amide 1 bands visible unmasked. Longer path lengths up to 50 micron can be used when the solvent is D2. Good. The good thing is you can have a smaller protein concentration, increase the path length without having too much of background contribution from D2O and still do a proper background subtraction, because you are well within the linear range of the detector and the D2O bending mode is not even there. Now, this brings about, as it says, this brings about a significant reduction in the protein sample concentration. Okay. Now, what are the finer details? Let us look at this real quick, and this is how we will end the class. The molar absorptivity order at 1644 centimeter inverse is about 22 mole inverse centimeter. This is a molar absorptivity, right. Okay. Now, as an example, let us take an example. The molar absorptivity of the protein lysozyme is 405 mole inverse centimeter inverse. This is per mole of residue. Residue means amino acid, per mole of amino acid in lysozyme. However, the net water concentration is much higher than that of the protein, right. Why is it so? You will see in soon, we will see it very soon. Let the lysozyme concentration be 50 grams per ml. Now, this is a pretty high concentration. Hence, based on the molar mass of lysozyme, which I have taken to be approximately 14 kilodalton or 14,000 daltons, the concentration of lysozyme at this 50 milligrams per ml is 3.5 millimolar. That is by no means a small concentration, that is pretty high. So, thus the water concentration, which is at 55 molar, because that is what the water concentration is still about 1.6 times 10 to the power 4 times higher than lysozyme concentration, because water is 55 molar and lysozyme we just saw was 3.5 10 to the minus 3 molar, right. Now, lysozyme has 129 amino acids. So, as I said, the molar absorptivity per residue was 405 mole inverse centimeter inverse. So, if you take this, so if you what you do is you take 405 times it by the number of amino acids, which is 129, this is the total molar absorptivity of the protein. Then what you do is you divide it by 22. So, 22 is what? 22 is the molar absorptivity of water. So, what you see is, now this is encouraging, right. What you see is that the protein molar absorptivity is about 2.4 times 10 to the power 3 times higher than that of water. Good. Why should we worry? This is why. Thus, at 50 milligrams per ml, you look at the next point. Thus, at 50 milligrams per ml, lysozyme has a total absorptivity of 182.9 per centimeter of path length. At 55 molar, now this is the key point. So, these two are the key points. At 55 molar, that of water is 55, it should be actually 22 anyway, it should be 22, by mistake I have written 20, is close to this. Now, though in the third point on the slide you had seen that the protein molar absorptivity is 2.4 times 10 to the power 3 times higher. However, the concentration of lysozyme is small and the net water concentration is very high. So, that actually overcomes whatever difference you have. So, here if you look at the last point says, thus for the same path length, that means if you are using the same path length, water still has 6 times higher absorbance at about 1650 centimeter inverse. That is where the amide 1 band absorbs. Now, no matter what you did, okay, no matter what you did, you increase the concentration to about 3 or 4 or 5 millimolar, that is a very high concentration. But you look at the concentration of water is 55 millimolar, you see you can see how much of contribution from the OH bend you would be having in this amide 1 mode. So, the amide 1 mode when you see would be the actual contribution from the amide 1 mode of the protein plus that of water, and that increases the total intensity. Okay. So, what we will do is, as you can understand, we will stop here in this class, but what you can take home from here is that just taking an IR spectrum is not so easy. there are some things you have to keep in mind. First of all, you got to make sure whether you are going to take the protein in water or D2O. If you have to do the protein in water, because sometimes people say that if you exchange with D2O, then what can happen is the protein conformation can change or some other effects can happen. So, if you want to do it in H2O, then you have to go for a very small path length, less than 10 micron. Companies like Bruker, Nicolette, they suggest 7 or 8 micron path lengths or even 6 micron path length cells, right. But then you can understand these are less than 10 micron, but what is the problem? The problem is, yes, the water contribution would decrease, but think about the protein concentration, how much you have to ramp it up by, and if you are going to ramp it up, you can have many other artifacts like protein aggregation and many other things coming in, right, which you do not want. Okay. And the other thing is, though the protein molar absorbance, that means the whole absorbance of the protein is higher than that of water, it is just the concentration of water which is so high, which is on the order of 55 molar, which makes it so difficult for us to do a proper background subtraction if we have a protein dissolved in aqueous buffer. So, that is why if you are doing a transmission measurement, then in almost all cases, if you would know that the protein is not going to get affected, which in most cases they are like that, then you would do it in D2O, right. However, if you do have to do measurement with aqueous solution, then what you will have to do is you will have to resort to ATR, FTIR. This is something we will take up in the next class, and that is how we will end our discussion on IR spectroscopy.